Analog and digital. We're going to look at the differences between analog and digital signals and how to convert from analog to digital and back to analog. Here we have a typical analog signal, a potential difference varying with time, the potential difference taking any value as the time goes on. This is a typical digital signal. Now only two values of potential difference are possible. This high value, often called on or 1, the low value, often called off or naught. So this is a digital signal. The everyday world around us is analog. Things can take any value. Computers talk digital. So to convert the real world into a language computers can understand, we need to be able to convert from analog to digital. We then need to come back to analog so we can understand the signal at the other end. To understand the process, we first need to understand binary numbers. You'll be familiar with decimal numbers, where we have a units column, a column 10 times bigger with the tens, a column 10 times bigger again with the hundreds. So for example, the number 352 is made up of 3 hundreds, 5 tens and 2 units. The binary system is based on twos, so this column is twice as big as the first column, this column is twice as big as this, and the 8's column twice as big as the 4's column. So the number 13 we could write as 1-8, 1-4, no 2's, and 1-1. 8 plus 4 plus 1 equals 13. Completing this table for the binary numbers from 0 to 10, we find that 0 would be given by no 8's, no 4's, no 2's, and no 1's. Number 1 would be given by no 8's, no 4's, no 2's, and 1-1. Number 2 by no 8's, no 4's, 1-2, and no 1's. Number 3 by no 8's, no 4's, 1-2, and 1-1. So 2 plus 1 equals 3, and we could write the number 3 as just 0, 0, 1, 1. Number 4 as no 8's, 1-4, no 2's, and no 1's. Number 5, no 8's, 1-4, no 2's, and 1-1. Number 6 as no 8's, 1-4, 1-2, and no 1's. Number 7, no 8's, 1-4, 1-2, and 1-1. Number 8 as 1-8, no 4's, no 2's, and no 1's. Number 9, 1-8, no 4's, no 2's, and 1-1. And number 10 as 1-8, no 4's, 1-2, and no 1's. With 4 columns like this, the maximum number we could get to would be 1-8, 1-4, 1-2, and 1-1, which is 8 plus 4 plus 2 plus 1, which is 15. To get to higher numbers, we'd need to introduce a 5th or further columns. Any extra column we add gives us twice the selection of numbers. We can have all the original numbers with 0 in front of them, and all the original numbers with 1 in front of them. That's why computer memories tend to go up as 32, 64, 128, 256, and so on. So here we have an analog signal that we want to convert to digital. First, I'll place a grid over the signal and label the y-axis with the binary numbers from 0 to 10. Now, what we'll do is at each of the vertical lines we will sample the approximate value of the analog signal at that point. So here at the start, the signal is closest to the 0001 line, so we'll write 0001. Here, it's closest to the 0100 line, so we write 0100. Here, closest to 0111, so that's what we write. We carry on with this along the whole of the signal. Now, in some cases, this will be very close. For example, here, our analog signal pretty much crosses at the 0011 point, so we have an accurate representation of the signal at that point. In other places, it may be some way from the line. For example, here, it is almost the midpoint between 1001 and 1010. So we have to decide which it is closest to. Clearly, the greater the number of divisions on the y-axis, the more accuracy we'll have in this case, but more information to be transmitted. This process is called sampling. What we can now do is send this string of numbers 0, 0, 0, 1, 0, 1, 0, 0, and so on to the computer. This is the string of numbers repeated. We could write this as a series of high and low voltages like this, where we have 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, and so on. This whole process is called pulse code modulation, or PCM. We have coded our analog signal into a series of pulses. That is our analog to digital conversion complete. We've gone from a potential difference which could take any value in our analog signal to a series of low and high voltages that a computer can understand. What we now want to do is get our analog signal back. Here I've reproduced the chart from earlier, and I've already added on the binary numbers that we found when converting the analog signal to digital. All I need to do now is mark out the position of these binary numbers. So 0001 will go here, 0100 will go here, and so on across the whole of the chart. If I now join these points with a line, we have something that at first sight looks very similar to the analog signal we started off with. If I put a copy of that original signal over the top, we can see just how good the match is. Earlier on, where the signal was a low frequency compared to our sampling rate, we have a very good match. However, here, where the original signal is a higher frequency, this detail has been lost. Also here we have a loss of detail, and here. So this shows us that where the signal frequency is low compared to the sampling frequency, we get good reproduction. But where the signal frequency is similar to or higher than the sampling frequency, we get poor reproduction. We could solve this problem by sampling more often, but that would mean sending more data. We also have a little mismatch here, where we had to choose this point as being either 1001 or 1010. We could solve this problem by having more levels along here. This would mean more binary digits, and so again would mean sending more information. The rate of sampling is a compromise between quality and amount of information to be transmitted. We must sample with at least twice the frequency of the highest frequency found in the original signal if we are to not lose detail. For a telephone, the sampling rate is about 8,000 Hz. As humans can hear up to 20,000 Hz, this means that we lose some detail. That's why you sound different on a telephone to how you sound in real life. But for a telephone, all we need to be able to do is recognize the person's voice and what they're saying. For a CD, we want to get all the information that humans can hear up to 20,000 Hz. Therefore, we need to sample at least twice 20,000 Hz. CDs actually sample at 44,100 Hz. And of course they're doing this for the left-hand speaker and the right-hand speaker. The range of frequencies found in a signal is called the bandwidth, and if we're taking frequencies from 0, this is then called the baseband. And therefore, in that case, the maximum frequency and the bandwidth amount to the same thing.